Hello, everyone. Good afternoon. Welcome to this webinar. My name is Neil Barrett, and today we're going to talk to you about using FRED for modeling time of flight systems, such as those used on LiDAR. So what we're going to talk about is a brief intro to time of flight, or TOF, simulation, the applications that it can be used for. And then we're going to take a look at the parts that we need within FRED to model a time of flight setup. We're going to take a look at that in a fair amount of actual detail, and then we're going to take a look at some kind of results that we can get out of our optical system, and then summarize what we've talked about. And then towards the end, we can have an open session where we can answer hopefully some of your questions, which you can post in the chat. So time of flight simulations, what are they? Well, time of flight sensing is a key technology in terms of measuring distance. So the distance r to some object is measured using the time t that it takes for light to make a round trip from the light source. So we have a light source over here. We're going to bounce that source off of the object that we wish to measure the actual distance of, and then the light returns to some sensor. And so this distance r we can actually calculate from the time that it took for our light pulse to travel that round trip. It's a very simple calculation. It's just the speed of light divided by 2 times the total time. The speed of light, of course, 3 times 10 to the 8 meters per second is what we normally think about. But in LiDAR applications, it's sometimes more helpful to recast that figure and think of it as about 30 centimeters per nanosecond. And the resolution of our optical LiDAR system, we can also calculate from this other function here, which is essentially where delta t is the time of the pulse. So that's the actual length of our pulse. That tells us what the actual resolution of our optical sensing is. So in this case, a 1 nanosecond pulse would give us a spatial resolution of about 15 centimeters. So that's essentially the core technology in terms of its very basic form. The applications for this are things like ground or even environmental mapping. So we can put a LiDAR system on an airplane or some other air-based platform and essentially take images of the actual ground and actually discern depth. And it's also used now on advanced driver assistance systems, or ADAS. So putting a LiDAR sensor on top of a car and using that to monitor how far away other things are from us. And it's also found its way into consumer tech also. So the iPhone 12 now has a time of flight sensor, and games consoles in the past, the Microsoft Kinetic from about 2013, moved from a stereoscopic camera to a time of flight sensor. So the applications are quite vast, but in terms of the actual simulation, in ray tracing, we typically have software which is independent of time. So we don't actually monitor the actual time that a ray is traveling for. And that actually prevents us from performing a time of flight calculation in some direct sense. So instead, we have to flip things around, and the FRED ray trace engine maintains a measurement of the ray's optical path length, and therefore we can actually create a time of flight calculation from taking that optical path length and dividing it by the speed of light, and that then gives us the time that that ray is actually traveling for. So in terms of a basic FRED model to look at a time of flight system, We need the following things, really. So we need an object scene. That's the items that we want to take some distance measurements of. And that it takes the form of some geometry in terms of the things that we need in our thread object tree. We also need some optical properties. So the items that we're going to shine our light on and see reflected light back from, that is going to be scattered, reflected light typically. So we need some scatter functions. We also need ray trace properties, which tell the actual ray trace engine what types of optical interactions can actually take place. And then we might also need some coatings. We need a light source to represent the optical source of our system. So that's going to take part in the optical source folder. We also need some collection optics, which is again geometry to take that scattered light that comes back from our scene and then maybe focus it on some imaging plane or just take that light and place it on some detector. So that's the other item that we need, is something to measure the actual power of our light coming back. And in Thread, we can use analysis surfaces for that. And then we also need some post-processing to extract distance from the ray path data that we have. And that's really where the magic lives in terms of being able to do this type of kind of calculation. So we're going to take a look at a fairly simple system, which is going to be our chessboard. And we're going to take a look at a flash type LiDAR system. So a single pulse of light illuminating the whole scene, and then basically making some measurements of that light, which is scattered back. So at this point, I'm going to pop over to Fred. So this is the model within Fred. So as we said, we would need various things in here, and we need some optical properties. So we have some optical properties assigned to our chessboard and also to the box that our chessboard is sitting within. So the optical properties in Fred, they all live in various folders in the object tree. So we have some scatter functions here. Now we're going to use some basic scatter functions in this model, but Fred has, I think, around 14 different ways to model scatter. We're going to use very simple ones just based on Lambertian scattering. So we have a model here, which is a black Lambertian scattering, which reflects about 4% of the incident light. And then we also have another one, which is white Lambertian scattering, which reflects 96% of that light. And these two models are actually assigned separately to the pieces here. So we've in our geometry for the optical model, we've got our geometry grouped into two different sub-assemblies. So the object scene here has a couple of different parts to it. There's the chess parts, which actually are the pieces and the board. And if I hover my mouse over here, I can see that these are assigned the white Lambertian scatter. I can also just open this up and take a look at the scatter property that's assigned to it in here. And then the box and the screen, they have the black Lambertian scatter property. So essentially, we're going to see more light reflected back from our chess pieces and from our box in this specific case. We also have a ray trace control set up. Ray trace properties are very important for making sure that the light is only allowed to do the things which we want it to do. So in this case, we have a ray trace property called only reflected scatter, which, as you see, only scatters reflected rays and no other options are actually allowed for that ray. And that just helps keep our model a little simple, just for the purposes of showing you something that we can demonstrate in less than 30 minutes or so. And we don't actually need any coatings. So we don't have any coatings defined here. And that's because in Fred, the power is actually allocated to the scattered rays before specular rays. So the fact that our scattering model already tells Fred how much energy is going to be reflected, scattered, and that's all we actually need in this case. Now, in terms of scatter models, when we have light scattering and taking lots of different paths, we want to make our optical calculation as efficient as possible. So we really want the light to interact with these pieces and the box and scatter back towards our optics that's going to measure our light. And so to do this, we actually use importance sampling. So in this case, we have importance sampling set up on all of our geometry. And if I just take a look at the chess pieces, for instance, in the scatter tab, I can see I have importance sampling set up to direct our light back to our ideal lens. So all of the light is going back to this lens entity, and I can show the lens entity that's in our receiver optics, and that's this little item just in here. I can just zoom in. So this is our lens. Okay. So the light goes to that. Now, if I just run a trace here, so I'll just trace all of my sources. I only have one source. If I trace it, trace finishes, so just under 2 seconds. This is tracing to a detector, which is actually set to allow us to perform analysis after the ray trace is done. So I can just choose this option here. My analysis gets done in terms of showing the actual irradiance profile that comes back from our scattered light. And in the output window here, I can see I've got around 725,000 rays. Fred has quite a lot of different choices in terms of allowing us to scatter light back towards targets. And some options work better than others in certain cases. So we're actually scattering light back to our lens. But if I take a look at the lens, you'll see that the lens itself, and again, just zoom back in, the lens volume that it seems to live in is this box. So some of the light will be scattered into the corners of this rectangle and won't make it through our lens. So we could actually choose to use a more efficient type of importance sampling if we wish to. So perhaps instead we want to aim rays back to a point in the middle of the lens with some small cone angle. And I've actually got that set up in a script here, which I can just apply. So I can say that 2 point is true. And then if I run this script, so run my embedded script, and now take a look at the chess pieces again, you'll see that now the definition of the importance sampling has changed from my script, which runs very fast. And it's now going to a point in our lens, so a point centered on the middle of our lens with a very small cone angle. And this importance sampling, and like I say, Fred has lots of different choices. Here's a bunch of choices. But this one, if I rerun my trace now, still takes around 2 seconds. But if I rerun my analysis on my detector, I can now see I've gone from 725,000 rays to 932,000 rays. Okay, so I've gained around 28% in terms of ray counts, making it back to the region of interest. So this is what the power looks like. If I right click here and maybe turn the profile lines off, we can make the detail in this chart pop out a little bit better by changing its scale. So if I rescale this to look at maybe log base 8 and don't show the floor, just finish it just underneath log base 8 and apply that, then you can see kind of this is where the power appears to come from in terms of our optical kind of sensor. So most of the light comes back from our chess pieces, but there's also some light coming back from the sides and the back of our box. So the importance sampling is a key part in terms of making sure the calculation is very kind of efficient. Other parts of the model we have, obviously we needed a light source. We've traced rays without explaining what our light source is. The light source here is a very simple, incoherent, uniform source that's 0.94 microns and 0.1 watts of power. It's tracing 500,000 rays. The collection optics that the light goes back to is a fairly simple, I'd say, kind of a simplified optical system that just consists of an ideal lens. And there's also this kind of annular geometry around that lens just to block light taking direct paths back to our sensor. So that's just something of a fairly simple baffle. The item that we're using to actually measure the light getting back to our image plane is a sensor here. So we're using a planar detector entity. So that's what measured our light power incident on it. But we also have an analysis surface attached to this sensor. So if I just open this up, we can see that this analysis surface is doing analysis based on the rays that are on our sensor. Okay, and there's some filters in here which are going to be used in the script that does the post-processing of data. Okay. So importance sampling does have a big impact, and we recommend that you take a look at the options that Fred has and maybe think about which ones work better for any given system that you have. So the magic of the calculation once the ray trace is done is looking at all of the data that came back and then figuring out what the optical path length was within that data. So all of this happens on our script. So our Flash system here essentially has a number of steps that our script goes through. So the script, I can kind of show it you here. If I can just get back to Fred. The script here is in this time of flight or TOF calculations, which is an embedded script in this case, which means it's part of our Fred file. But of course, we can also have scripts running on a standalone basis too. So if I open this script, you'll see that there's quite a number of things. I zoom in a little bit. There's a number of things going on in here. So we won't go through the code in a huge amount of detail, but we will talk about what the basic steps that are going on within this code. Okay. So the first thing that we do is that we take the ray buffer. So at the end of our ray trace, Fred knows where all of our rays are, and all of that information lives in the ray buffer. And what we do is we first of all tell Fred to take the ray buffer and slim it down so that we only keep rays that are on our surface of interest, which happens to be our optical sensor. So all the other rays that happen to be on other optical surfaces at the end of our trace, we get rid of those. We then loop over all of the rays within the ray buffer with the intent of extracting what the minimum optical path length is and what the maximum optical path length is. And those are essentially going to form our outer ranges that we're then going to scan within. So once we've found that minimum and maximum, we can then loop over our ray set, filtering by an optical path length range. So we could take that minimum and maximum, maybe say that we want 50 different spatial measurements within that range, and then loop over that ray set. And within that loop, actually several things happen. We calculate the irradiance for each optical path length segment, and we save that data to something called an ARN, which is an analysis results node. And those ARNs are going to be used in the main calculation of the time of flight, but they're also going to be used in terms of figuring out a nice movie file and things like this. We also then save the optical path length and save the total power at that optical path length to some arrays. And those things are going to be leveraged to generate our 2D plot of power versus time. And then the original ray buffers can then be removed from our system because we have all of the data that we need at this point. So Fred will then, in the script, it will plot the 2D time of flight chart, which is a sub-function. It will create our movie, and then it also loops over the ARNs. So all of these slices of optical power per path length, it loops over those. It starts with a blank template of data, sets all of the data within it to the shortest optical path length, and then loops over all of these slices of optical path length data that we saved. And for each cell it finds with a non-zero irradiance, it sets that cell to the current optical path length. So essentially, we build an image of optical path length looking from the furthest item detected back towards the first object detected, and that then allows for optical occlusion effects. Okay, so that's essentially what our script does. These are all the items here. Like I say, we perhaps won't go into too much of the detail of the individual parts of this, although if anyone has any questions at the end, then we certainly can. But right now, I'm just going to run it. So if I go back to Fred here, I can run my script from right-click and run embedded script. And in the output window, it tells me that it's extracting the range data. It finds the shortest and the longest optical path lengths. And now it's creating arms. And if I expand this out for us whilst the script is going, you can see it's actually calculating irradiance per some distance of optical path length. Okay, so these are the slices of data it's taking. When all of the data slices are done, it then calculates this time of flight calculation and then calculates the 2D distance plot, which I can again just go to this plot individually, turn off the profile lines. And so this is a plot of distance, and this is the X and Y location on our sensor. So this is essentially where the image is formed. So you can see that the maximum distance is around 310 millimeters, which is colored here in dark red. And then the shortest distance is around 189 millimeters, which is kind of this point here. Of course, I can click on my chart and actually Fred will tell me what the distance is down in this bottom left-hand corner. This chart is actually generated using a nice color scheme, which we'll talk about in a bit more detail in a moment. But first of all, the 2D chart. So this was one of the data that kind of the script gave us. So this is the power in milliwatts versus time in nanoseconds. So this is taking that optical path length and converting it to time. So this chart actually has kind of 7 peaks, 7 kind of large peaks. And these are each of the chess pieces. So this is the furthest piece on the chessboard. There are 6 peaks, 1 for each piece on our chessboard. And then there's a peak at the front here, which is that screen that is around our box. That's the first reflection before we actually get to the pieces on the chessboard. If we converted this time axis to a distance measurement instead, then that would give us some kind of 1D range-only plot. Okay, we also have a video that's made for us. So this is essentially what each of those arms are capturing. Every single slice of the arm data that we measured for a certain optical path length is kind of here. And so Fred has calculated this with a single line in our script using this function on save to video, pointing at all of those slices of arms that were made. Okay, so this is kind of a neat feature within Fred. And you can see if I just play this actually, so there's the front pieces as the light goes further on. As it gets to the end, if I just stop the video there, you can see actually shadows of the other pieces that are in front of it on the board. Okay, so that's kind of a nice nice little graphic. And then in terms of the actual 3D map of the time of flight calculation, in terms of the distance measurement, this is that kind of plot that I just showed earlier. This uses a new color scheme in Fred called Turbo. This was added a couple of months ago and is going to be available in the next version of Fred. And this color scheme was actually developed by Google AI Labs. It's very good at bringing out depth data, which is why it was used here. The color schemes that you have, you get to choose. I mean, this one is coloring the closest item blue and the furthest item red, but we can change these items. So if we go to the chart color levels, we can say, well, actually, maybe we want 50 color levels, which makes our chart a little smoother. We can also change our color level style here, so we can maybe choose the inverted turbo scheme, which then has the closest items in red and the furthest items in blue. The chart style files are just text files, and you can create your own, or you can change them around and have some fun with them. So another thing that we sometimes see in LiDAR plots is the color scheme repeating over certain distances as well. So I actually took the turbo color scheme, and I did that by creating a new version of it, which just interlaced some of these values. So now it actually goes through to blue and then restarts at red again. Okay, so that kind of color depth is now over some longer distance. So this was a very simple example just of a chessboard, but of course we can also take a look at more complex files. So in this case, this is a more complex model. These are all CAD objects of some kind of street scene with some people walking along, and we have a car here with its LiDAR on top. If I just isolate this feature, we can see the kind of that's that part of it. Actually, I can just isolate the whole thing. So that's the kind of CAD housing that sits on top of our car there. And then once we kind of have our scene, we can shoot our light out, reflect it back. And this calculation took a little longer. This was a 2-minute calculation, so I won't run it a second time here. But that brings out kind of a lot of detail in terms of our CAD, sorry, our kind of our image there. This is only, again, using a certain number of color levels, only 25. In this case, I could potentially go to my interlay scheme and choose 100 levels. Okay, and then you get quite a lot of detail brought out this image in terms of where things are, all these little windows and little details. And there's a bunch of things we can also do as well. So Fred's charting has some advanced options in here. So if I go to the advanced tab, and in the chart group area, I can choose, actually, this is going to be a contoured plot. And if I choose the contoured plot, then you can see all of these edges brought out in color depth of all of the various items. Okay, so the style files are very flexible in terms of being able to visualize data, and also the Fred charting are also very flexible in how we visualize data, which is obviously a key part of understanding what's going on in our optical system here. Okay, so that's what we just had there. So that's pretty much us done for our 30 minutes. So the summary here is Fred can model time-of-flight systems, and we do that via using optical path length as a proxy for time. Fred's options for importing geometry in CAD and defining scatter functions and various ray trace properties and sampling are all kind of important. Sorry, I missed a word off the slide there. And Fred's powerful yet simple scripting language enables us to collect data from our ray trace, manipulate that data very easily, and then present it in a way that's very nice for time-of-flight applications. So that's the end of the formal presentation. And at this point, if anybody has any questions, we'd be happy to answer them.